and mass. Okay? Because the thing about chapter 4, which by the way is called Newton's laws. So chapter 4, now we're going to be studying Newton's laws. All right? Thanks to this, we are able to launch rockets to outer space, for example, right? The reason we know rockets do that type of motion I've been explaining, or we can study free fall, and we understand free fall, is because of Newton's equations of motion. Or Newton's technically four laws, because there is the three laws of Newton and the gravitational law, which is normally considered his fourth law. So imagine we have the ground here, and you have two masses, M1 and here M2. According to Galileo and therefore Newton, if they are both released from the same height, they will reach the ground at the same time. You guys should know that now because they both are at rest, by the way. You remember for free fall, that, right? That's the equation for free fall. But what is free fall? Free fall is the idea of objects falling towards the ground due to the action of just one force. That force is the force of gravity. So what is a force then? Why do we call it the force of gravity? Because objects of different masses, they have a different gravitational pull. The gravitational pull on M1 and on M2 are different because M1 and M2 are not the same. So I'm going to make M1 less than M2. All right? So M1 can be like the feather or cotton. M2 can be wood or iron. Right? The feather and the hammer. In the absence of air friction, they will reach the ground at the same time. So they both have different masses. Why do they reach the ground at the same time? Because the force that is acting on M1 is its gravitational pull, which we call it the weight. This force I'm drawing down, that is the weight of M1. That's the force M1 is feeling, which is making it fall towards the ground. On M2, the same. Weight 2. So weight is not mass. Weight is a force due to gravity. While mass is the amount of matter in a given object. All right? Mass is the amount of matter. Weight is a force that only happens because of gravity. Okay? So, mathematically, what is weight? Weight is the multiplication of mass times gravity. We have said W equals to mg. That's what it is. So this will be M1G and W2 will be M2G. And that's the only force acting on the masses. So then the question remains, why are they falling at the same time? We have the equation of motion for height. Since gravity is the only acceleration for both masses, they will reach the same height at the same time. Now, if I want to use Newton's laws, and I'm going to go farther ahead, all right, for objects accelerating by a unique net force, some of you probably know this already, but the net force acting on a body is equal to mass times acceleration. This is Newton's second law. So this is M1A. This is M2A. So I cancel the masses. Gravity is the acceleration for both. Since gravity is the acceleration for both, they both reach the ground at the same time. That's the force sort of explanation for free fall. All right. So that's how I wanted to introduce chapter 4 by showing you guys the difference between mass and weight, which you're going to need tomorrow. Tomorrow, you're going to do the force stable experiment. So you're going to be given masses. The masses can be measured in grams. I want to show you this, okay? So you're not going to use this maybe tomorrow, but this is a mass, right? There, you have the hook in there. This is a mass of 1,000 grams, 1 kilogram, this. So if you're giving a mass of 1 kilo, that's not its weight. So tomorrow, you're going to be using different masses. Let's say that tomorrow you select a mass of 1,000 grams. 1,000 grams, we know that's 1 kilogram. That's the mass. What will be the weight? Which is the force due to gravity. Its weight will be 1 kilogram times gravity, 9.8 meters per second squared. You know what this gives you? Oh. So this will give you 9.8 newtons. Newtons is the unit for weight, thus the unit for force. So the units for force are newtons. Well, it makes sense, right? There. That's the force, that's the mass. So then there's a question, right? Why do the astronauts limp when they were on the moon? If you have, I hope that you guys have watched videos or at least movies of astronauts, first of all, carrying a lot of weight because those suits are really heavy, and there's a reason they are heavy. It's because, for example, on the moon, right? On the moon, gravity is very weak. Gravity is about a sixth of the gravity of the Earth. So it's about 1.6, 1.5 meters per second squared. It's very weak. So, for example, this mass on the moon, right? So a mass of 1 kilo on the moon will have a weight of 1.6 newtons, much less. So that's why astronauts, they have to limp forward. right? Which is the reason why they have to use heavy suits. It's one of the reasons, it's more than that. So they can add more mass. The more mass, the more weight, the easier it is for them to actually walk on the moon. All right? So there you have it. Mass is the same on the moon and on Earth, but the weight is what changes. Okay? And eventually we can use this and Newton's laws to explain free fall of astronauts orbiting the planet in the ISS or the Earth orbiting the sun. There are forces in between the Earth and the sun. We call that the gravitational force between planets or a planet and the star. And that's the reason the planet goes in an ellipse, by the way, not circles. Planets go around the sun in ellipses, okay? And if you know something about ellipses, the sun is located at one of the focus. Now, the thing is that due to the orbit of the planet itself, due to the distance, the orbit, and in general, due to how close the Earth, Venus, Mars are to the sun, their orbits are very circularish, right? If you look at the orbits from the top, they are ellipses, but they are not very elliptical, right? A planet that has more ellipticity in its orbit is Mercury. But Mercury, there is another reason, right? You probably know that this is, or right now I'm showing you Newton's view of gravity, right? Newton's view of gravity is basically what I've been saying, a force, right? So this pen falls towards the ground because there is a force between the pen and the earth, all right? However, to explain the orbit of Mercury or to explain exotic objects in the universe, like for example, neutron stars, black holes, quasars, right? And other extreme situations, right? We cannot use, we can't use our understanding of gravity as a force. We have to use what we know as the Einsteinian view of gravity, which explains gravity as a bend of space-time. But that's a topic for astronomy. So if you're interested, take astronomy class because that's where I teach basically Einsteinian gravitational and then the whole idea of relativity. All right. But for now, we just talk about forces, weight, masses, and Newton's laws. So that's the introduction. All right. What I'm going to do now is I'm going to give you a 10-minute break. And then you guys will come back to show you the PowerPoints and do some examples. All right. Because the theory is not a lot, but there are quite a few examples that we're going to go over between today and tomorrow. All right. So it's 7:07. We come back at 7:17. All right, guys, let's continue with this. Okay, it's actually good that we have this. So, are there any questions, by the way, with what I was explaining about gravity, weight, mass, forces? Okay. Let's see here. All right, so look at the following. Look at the following picture in front of you. And by the way, we are going to be talking about free body diagrams, which is a very important section of chapter 4, right? What you are seeing there actually is a free body diagram or a forces diagram of a body that is moving towards the left. So, as you can see already from the picture, we use vectors to illustrate forces. You have a mom and a dad and their child, right? They are both pulling the sled at angles of 35 respect to the horizontal. Now, why is the body moving towards the left and not up or down? Well, take a look at the magnitude of the forces. Both are 55, and both are at the same angle with the horizontal. So if you break, and that's going to be important, right? We're going to be using vectors, so we still have to use our vector component, sine and cosine. So if you were to break each of these forces into horizontal and vertical, you will find that the vertical component of this force is identical to the vertical component of this one, but in opposite directions. So they cancel out. So the net force is acting towards the left. What is 57? Is anybody familiarized with concepts of forces? If you are, then you probably know what 57 is. There is a name for that in this chapter.
Is it Newton?
Huh?
Is it Newton?
The what?
57 Newton?
No, but what is it? There is a name for that force.
Drag?
Yeah, not bad. I mean, okay.
Is it opposing force? The opposite force?
The technical name will be friction force.
Friction force.
Friction force, yes. So we're going to be talking about that, right? At the beginning, we're going to ignore friction, but to make things more realistic, eventually we're going to introduce friction into the mix, right? Friction is the reason why objects don't keep moving eternally, right? So the friction acting on the sled is 57 newtons. Now, the body is still moving towards the left because both forces, right, eventually they overcome friction. If you overcome friction, you end up moving. There is a net force. If there is a net force acting on a mass, then there is acceleration. How do we know that? By Newton's second law. All right? Which is kind of what I introduced in the previous, on the board before. So these are the main topics of chapter 4. I can already explain this, right, on the whiteboard and wait, but we are going to be mainly discussing about Newton's first law, Newton's second law, Newton's third law, and then the nature of forces and free body diagrams, which is what I was doing on the board. I will explain how and why it's important to know how to draw forces, because at the end of the day, to solve problems on chapter 4 and chapter 5 and so on, now that we're going to be dealing with forces, masses, weight, and etc., we need to know how to do a proper free body diagram. All right. In fact, there, a force is the action of pulling or pushing. Force is a vector because it has magnitude and direction. And the units of force, as I said, are newtons. Now, in some cases, like in the case of the sled before, and this is another one, you may have a person pulling or pushing an object with a force making an angle. Sort of like when you push or pull your luggage in the airport, right? You normally do it at an angle. And we do that to reduce friction. Okay? When we start discussing more about friction, you will know and you will realize why that's the case. So, as I said, mass is the amount of matter in an object, but that's the chemistry definition of mass. Physically, mass has more meaning. For example, if we talk about inertia, the more mass a body has, the more inertia that body has. Mass is also the measure of how hard or how easy it is to change an object's velocity. The more mass, the harder it is to accelerate an object or to stop it. Imagine a bowling ball, imagine a beach ball. Now that it's summer. If they throw you a beach ball, you can just catch it. If they throw you a bowling ball, it's harder to stop. Why? Because the bowling ball has more mass. Therefore, it's harder to stop it. The same can be said about inertia. When and how do you guys experience inertia? Easy. When you brake all of a sudden. Imagine you are driving on the road, right? And you have to stop for a red light or on an intersection. If you are going too fast, you're going to lean forward. Why do we lean forward? Because of inertia. So mass and inertia are related. And by the way, that introduces Newton's first law. Newton's first law is also known as the law of inertia. And it's basically this. A body will remain on a state of motion unless a force acts upon it. In the absence of any external force, an object will keep moving at constant speed in a straight line or remain at rest. For example, this mass, right? You can see it there. It's there, it's not moving. But if I do this, I'm pulling it upwards because I'm holding it, I'm pulling it. If I let it go, it falls because of the force of gravity, because of its own weight. So that's the force acting on the mass. If not, it stays there. Now, do objects really remain moving at constant speed? Because of friction, that's not really the case, realistically. But there is a situation where when you accelerate an object, it can remain at that constant speed, moving from point A to point B. That will be in the absence of air friction, in the absence of friction, in the absence of drag. The best case or the ideal case will be in the vacuum of space. You see, if you launch a rocket with an escape velocity and it leaves the planet, once it reaches outer space, it can remain freely moving at a constant acceleration or at a constant speed because there is no friction anymore. Unless, of course, the object encounters, a planet or an asteroid or a star. But you probably know about the Voyager, right? The Voyager 1 and the Voyager 2 were non-tripulated missions launched in the 1970s to explore Jupiter and some of its moons. But because of this that I told you, the Voyager explored it, it flew by Jupiter, and then it kept moving until it left the solar system. And we know now, even till now, it's still moving and moving away from us. Why doesn't it stop? Because there's nothing to stop it. There is no other forces acting on the space. There's no friction, right? So that is the first law, or Newton's first law, which again is also known as the law of inertia. All right. Newton's second law. In order to change the velocity of an object, a net force is required. Well, the example of the masses, right? You know already that if I let it go, this mass is going to reach a final velocity when it touches the ground. So the velocity is changing. Why? Because of gravity. And what's gravity? An acceleration. And because of gravity, we have the force of gravity. So that is a force which is making this pen accelerate towards the ground. So Newton's second law is basically F equals to ma. F is the net force, mass is the mass, A is the acceleration. So that is the thing though, right? If you write the equation F equals to ma, if you make the mass larger, the acceleration will decrease for the same force, if the force is constant. If you lower the mass, the acceleration increases. That's why the physical concept of mass is that value of an object that is making the acceleration harder to produce. All right, this 1 kilo is probably around 400 grams. So I can move this easily, but this is harder to move. A little bit harder, it's only 1 kilo, right? This object is easy to move forward, right? On the table, like that, but this mass is harder to move. See that? Now, of course, there's friction, but still, right? For the same force, this will accelerate less than the water bottle. It's plastic. All right. So that is Newton's second law. And I'm pretty sure everybody in class knows Newton's third law, because Newton's third law is always mentioned in real life. Do you guys, who can tell me what's Newton's third law? Hmm?
For every like motion, there's an equal reaction back.
Yeah, good. For every reaction, there is an equal and opposite reaction. Very good. Yes. That's basically what you experience when you punch a wall, right? Or I mean, this example of shooting well, yeah, if you the whole idea of recoil, right? I'm gonna assume that not many of you probably haven't done it, but in a shooting range, right? Why there is recoil? You probably have heard about that, movies or even like real life examples, right? In math, that's the idea of you leaning backwards, right? When you shoot a gun. And why does that happen? Because of action reaction. Okay. Or when you observe rockets, if you have seen rockets being launched from NASA, you see the explosion of gases, right? That's the action. The reaction is to pull the rocket upwards. Action reaction. Okay. Now, what do you have in front of you? Just to keep talking about Newton's second law. You have different weights, right? Or two equal weights exerting twice the force of one. So you have one weight here can be 1 kilo. So that will give you 9.8 newtons. 2 kilos will give you 19.6 newtons. double the weight. Okay? And these springs, by the way, that's a device that you can use in real life. Okay? We can use them to measure the mass of luggage. Right? They look like that, like a hanger. You use it, you leave your luggage, and it will tell you the exact weight. Now, if you think carefully, right? In real life, we use kilos or pounds, and we call that weight. That's because that's the convention. All right? The weight, for example, of a person is not 60 kilograms, or in pounds, 145 pounds. That's the mass. The weight will be by multiplying the mass times gravity. Okay? We call it weight because mass is more a scientific term. It's more a science term that we use in chemistry and physics. Right? But now you know the difference. So like I said, acceleration is proportional to the force. The more force, the more acceleration. If you double the force for the same mass, you're doubling the acceleration. All right? Like I explained before, acceleration is inversely proportional to mass. The more acceleration, the less mass, and vice versa. All right? And here is the equation. That's the equation we're going to be using. You can write it in terms of A equals to F over M, or F equals to ma, where m is the mass in kilograms, acceleration is in meters per second square. All right? That's the vector form of this equation. Remember, force is a vector. So if we have forces acting in different directions, we need this because there is the net force. This symbol here means the sum. So the sum of the forces acting on a body, that gives you the net force. The net force acting on a mass is equal to mass times acceleration, where the acceleration is on the same direction as the net force. All right? And there are your system of units. SI units, kilograms, CGS, grams, British, the slag. All right? We're going to just use SI units. So, and here's some examples of typical forces. Look, for example, the thrust of a jet engine, 75,000 newtons. To accelerate a car, 7,000 newtons. To stop a car will be the same, about 7,000 newtons. Right? So, 7,000 newtons is a lot. Right? 7,000 newtons would be like the mass of a 700 kilogram person. So can somebody explain why a truck driver can stop a truck? It's hard, but they can do it. And trucks are really heavy. Like they're very massive. How does a truck driver manage to stop a car? Oh, let's see. There is a lot more of mass in the truck, so the momentum is bigger compared to a tiny car. Yeah, but I'm not talking about momentum right now. I'm talking about how is it possible for the truck driver to exert that level of force with a brake?
Like through hydraulics.
Nice. Okay, so that's good. I'm asking questions that to explore how much you know of physics. Yes, that's what we call the Pascal principle, right? When you press a brake, you exert some pressure through the system, the brake system, that allows you to, with a tiny force on the pedal, exert a larger force on the brake that is stopping the tires. Basically, the car from moving. That's the hydraulic system, or in this case, the Pascal principle. We may talk about that at the end of the course, all right? But that's basically the idea behind a brake system. So very good. Very good. So you know, some of you guys know about that. That's good. Okay, so let's close this. Okay, so now we can go into free body diagrams. Let's see here which slide am I. So free body diagrams are basically this, or what you saw before, here, or here. Is the idea of, depending on the situation, draw the forces acting on a system. Why do we need that? Because, and today we're going to be exploring different situations. You can have situations where a mass is in equilibrium, so not moving, or you can have situations where the mass is moving. But to know whether or not the mass is moving, we need to know what and in what direction the forces are acting. And by the way, that's probably close, but that's what you guys are going to do tomorrow. So tomorrow you're going to be given a table and you're going to hang forces. And you're going to have a ring at the center. The idea is that you guys find the right positions to make sure that that ring is in equilibrium. All right? So with today's class and tomorrow's lab, you're going to have a full circle understanding of at least free body diagrams like that and forces. By the way, that's Newton's third law, right? Forces always come in pairs. If object 1 exerts a force on object 2, then object 2 exerts a force on object 1. So here it is. Right? If you are pushing an object, or if you are braking a car, or satellites, or even planets between each other, right? There is a force acting from the Earth towards the moon and vice versa. And I think I explained this in class. Due to that force, the Earth tilt wobbles a little bit, but it's so tiny that we ignore it, right? Now, before I do the examples, right? Planets orbit the sun, and then we have the moon orbiting the Earth, and we have other moons orbiting other planets, right? The reason why they seem to be, or they are in a sort of harmony, right? Which is what confused the Greeks and made them believe that the Earth was the center of the solar system or the universe. They believed that there was something called the harmony of the planets, right? Where everything actually fit together. One indication that the Earth wasn't the center of everything was when we look at the moon, and then we look at other planets like Jupiter, who has its own moons. Galileo did that. He observed Jupiter, and he noticed that just like the Earth, but more, it has moons orbiting it. So that was the first indication that there wasn't really something special about the Earth to make it the center. And the major source of evidence for the Earth not to be the center of the solar system was the fact that as we orbit the sun, other planets are orbiting it. Venus, Mars, and we can track their motion. And the thing about tracking their motion is that at some point we notice Mars retrograding, like going backwards. That's not possible if the Earth was at the center. The reason Mars seems to be going backwards is because as both planets orbit the sun, the Earth overtakes Mars in its orbit. So it looks like it's coming to us. And that can only be explained again with what we know as the heliocentric model, the sun at the center. Okay, so now you guys know about forces, so I can explain and show you free body diagrams, all right? Let's start with this and then I show you the whiteboard. So here you have a book being held by somebody's hand. And there are two forces that you consider. Action, reaction. The action will be W, the weight. So what's the F? What's the F going up? That's the force that you are exerting towards the book, right? If I hold this mass, I can feel the weight of this mass. That will be W. But by Newton's third law, my hand is also exerting a force towards the mass, upwards. All right? We call that the normal force or reaction. Now be careful because normal forces, they come in a variety of ways, and I will show you that with some examples here. But now let's show you the free body diagrams and how you do them, and then we can start doing some examples, all right? I will start with equilibrium, and then we can go a little bit with acceleration, and then there are some situations like, for example, that. You see, that's a simple mechanic situation where you have a pulley. And then you can have these two ropes holding a mass and an inclined plane, right? So those are all situations that you're going to be learning, all right? Let's just check that this is... Okay, it's recording. So like the book example, you're given a mass, you know there is gravity. So you draw the force down. That's the weight, which is mg. And by action reaction, there is a force. Now I want to call it the normal force. Why do we call it normal? Because the normal force is always perpendicular to the ground. Okay? You're going to see when I do it here. Here is easy. Action, reaction. Okay. Now, normal forces only appear for objects that are on the ground, or if I'm, for example, leaning towards the board or towards a wall, there is a normal force from the wall towards me. But what about objects like that? You have the roof, two ropes, and you have a hanging mass. And again, it's not moving. All right. So we have a mass, gravity, you have the weight, mg. That's the weight. There's no normal, but the mass is connected to a string or another rope. Because it's not moving, just like the hanger I show you, this string or rope, there is something called acting on it. That's known as the tension. There's a tension on this rope, and on this rope. The tension is like the tension of your muscles. If you do weights in the gym, you experience something in your arms. That's because you're exerting a force. So your muscles are stretching. When you stretch something by external force, that's tension. So there is also tension here. How do you draw it? It's an extension, right? So you draw it like this. Tension. Like that. Okay. What about these ropes? There is also tension. But this rope is at an angle of 45, this rope is an angle of 30. So the tensions are not the same. This is T1. This is T2. Why are the tensions different? Because the angles are different. So that's your free body diagram for this. Furthermore, what can I say about this mass? Because it's not moving, for this hanging mass, the value of the tension is equal in magnitude to the weight of the mass. That's because it's not moving. We want to solve a problem, don't worry. I'm just showing you some details of this free body diagram, all right? But again, the idea of a free body diagram is to identify what forces are acting in the system, all right? And in particularly on a given body. So this weight, tension, and the tensions here. These tensions here affect this. They're the reason why it's not moving. All right? Okay, inclined planes. So what do we have here? So we're going to assume there is no friction. Oh, yeah. We're going to assume there is no friction. So this mass is it can be moving, all right? Or I can find an angle. I can find an angle where the mass is not moving. For example, there, right? This. So I have a mass, and that's the inclined plane. So I just find an angle where it's not moving. Right? Now that's due to friction. So we're gonna do first the case of what forces are acting here. All right. Gravity is always pointing down. So I draw mg like this. The mass is on the inclined plane. So there is a normal force. But now it's not like this. It's not horizontal. Now it's inclined. Normal forces are always drawn perpendicular to where the mass is sitting. So if the mass is sitting like this, my normal force goes like this. That's my normal. And it makes 90 degrees. So in a real case, the mass will accelerate, right? I put that in here. Let's do something else. Like this. So why do objects fall in an inclined plane? You see, I can continue extending this. I have a right triangle here. And I can continue extending this. Another right triangle here. By geometry, that's theta. That's 90 minus theta. So this angle is also theta. Aha. So I have this. So I want to draw it here so you guys can see it. All right. I have the vector weight. And I have this. And of course the angle here. I'm going to break this into components. The component this, the component parallel to the inclined plane. So I will find this component and this component. If you remember what we did, this is just like the projectile motion, but upside down. That's the adjacent, that's the opposite. So this is mg cosine theta, and this guy is mg sine theta. So this is why. This is why the body is gonna fall. Because there is a force. I'm ignoring friction. If I'm ignoring friction, that's why the object will end up falling. And this is mg cosine. Okay?
I have a quick question.
Yeah.
Yeah, because I was a little confused when I was doing this part. Why does it switch to be the mg cosine theta? And like, because is that technically not the I'm sorry, the y-axis on that type, or does it change in this type of problem?
If your axes are x and y, you can look at this, and yeah, this will be like your y-axis, this will be your x-axis, right? The reason is because now the angle is not, you're not using that angle per se. You're using the angle here, this one. So if you remember when we did projectile motion, right? We always had this. Now I'm twisting it like that. So now this is the, well, this is now the weight. This is here. And then this goes here. And this goes here. We call that, some of you probably seen this, rotation of axis. That's one of the last topics in pre-calculus. Your x and y axis, you can rotate them, right? So that's what basically what you do. You rotate the axis, so then this coincides with this, and this coincides with that. That's why this is like your y, and this is your x now. And since that's the angle, we can break it into components. mg cosine, mg sine. That's why it changes. Graphically and mathematically. Do you see it or not?
Yeah, I mean, I understand how you're getting them, just because of like the properties of the triangles and stuff, but I just didn't understand if we were still viewing like the axis as y is as the mg cosine being on the y-axis, or if it's technically changed into the x-axis.
You are, but remember, the axis have been rotated. That's why. So that's your y, that's your x now.
Okay, I got you.
Yep.
All right, thank you.
Yeah, so there is a whole mathematical background for that. You can also translate axis, by the way, so you can translate and rotate. But the idea behind that, the main idea is that your y-axis can be changed to a more convenient position to actually find the components. Inclined planes is one example of that. And I'm gonna be honest, there's one example I didn't do on projectile motion that includes this. You can actually have, and there's an example, I don't think it's in the book. It's in one of the textbooks I have here, but you can launch a projectile like this. And it's not as simple because, and the reason we don't do it in this course, we could, is because if you have a projectile in an inclined plane, both components are not constant. The x and y change because you see gravity is like this, right? But you can also break gravity into components. So guess what? Gravity makes the object move forward and up and down. So if you have a projectile motion, right, in an inclined plane, both x and y have acceleration. That's actually a very interesting problem, though. But I mean, just to show you how this angle can change things. All right. For now, let's just focus on the force and then this. Eventually, we're going to use this because we're focusing on this. This is the reason why the object accelerates. the object is not moving up and down. So the normal is equal to whatever is going downwards, which is this. So mg cosine is basically the normal force. All right. Don't worry, we're gonna do problems using this in a little bit. So that's one situation. So that's your free body diagram in an inclined plane. All right. And then we have pulleys. You guys are gonna be doing an experiment with pulleys and one like that. Right? Monday and Wednesday, actually. We're gonna do the Atwood machine, which I'm gonna show you as well. And you're gonna do the table. All right. And that's good because that's gonna be in the exam. So for the pulley, we're gonna consider no friction in the pulley and ideal, and you have a system of masses. So obviously M2 is gonna drag M1. Why? So what forces, so let's test you guys based on this. What forces are acting on M2?
Wait.
Gravity.
Okay, so let's draw that. What else? We're focusing on M2 right now. What else is acting on M2? Look at the examples I just did on the board.
Normal force?
If the object is hanging on air, there's no normal.
It'd be tension.
Tension on the street, right? Tension on the road. So tension. Okay, that's it. Now M1. What's making M1 go to the right? Hmm? Well, let's start with the easy one. What are the forces acting on M1?
Normal.
Huh?
Normal force.
The
So the-
normal force. So if there is normal, what else do you draw? Action. No, that's a reaction. What's the action? What?
Wait.
Wait. Yep. And what's the other force acting? What's making M1 move to the right?
M2 is being pulled by gravity.
This tension. The tension on the rope. Because the pulley is ideal, the tension is the same on both parts. All right. So those are examples of free body diagrams, guys. You identify every force acting, and depending on the situation, we solve for what they're asking us. And that's what we're gonna do now. Now we're gonna start with some examples. First, I will give you an example on equilibrium. Let's actually do this. It's a classic example, all right, of equilibrium. And you're gonna see how much of vectors. And actually, it's good because you're probably gonna have to do this tomorrow. Yeah. So pay attention. You're gonna need this, okay? And then we can do one like this and an inclined plane. We will see, okay? Because now there are many different situations, okay? Which, by the way, that's why I strongly recommend you guys watch the video I have already uploaded in Canvas, where I go over examples of this. All right. So let's start with some numerical situations. So, example here. If you're given, again, the ceiling, you're given one rope like this, one like that, and a mast hanging. This mass is of 20 kilograms. And the angles here, let's make this 45 degrees and 60 here. If the system, so here, if the system is in equilibrium, if the mass is in equilibrium, calculate the tension on all the ropes. All right. So you have a mass, right? Hanging in there, in equilibrium, so not moving. Find the tension on the free ropes, all the ropes. Interesting, right? You're not giving, you're only giving the mass and the angles. And of course, no gravity. So this is when you have to, when I used to be a student, when I went from motion to this, and even vectors, there was a transition I had to do mentally. I was used to just, use the equation and find the acceleration. The transition is that now, for this type of problems and for the next chapters, you have to think about what's happening and you have to look at the picture and you have to do some critical thinking before jumping and applying. Well, there's no formulas actually, right? I mean, F equals to ma, but there's no acceleration. So you have to think about the concept, right? And that's what makes physics a bit challenging for some students. Sometimes some students actually click it, right? That now it's not just about the formula. It's about, okay, I'm given this situation, I'm being asked about the tensions, and I'm only given this. And there's no, I cannot use an equation sheet because the only equation is, in this case, is mg for weight. So how do you solve this? Well, for any Newton's laws problem, especially for the ones in equilibrium, you're going to start by doing the force, the free body diagram. Okay? So, just like I did, we're going to draw the forces acting in here. So, what's this?
Wait.
Weight, which is, let's call it W, equals to 20 times 9.8. What about here? We have a tension, right? Let's call it T1. And we have and we have two ropes here. Different angles, therefore, different tensions. T1, T2. All right. So that's the first thing you have to do. Draw the tensions, right? Caramba. T2 and T3, sorry. That's T1. So now I know that this is what I'm being asked. T1, T2, T2 and T3. Okay. Directly. Well, first of all, how much is 20 times 9.8?
196.
Newtons. That's the weight of this guy. So directly, because it's in equilibrium, because of equilibrium, what's T1?
Should be the same.
196.
196 newtons. Very good. Okay. Now we know that T1 is 196. And you see why the directions are important? Because now I can do this figure. Let's draw this only now. I have my X and Y axis, T2, T3, T2, T3, and this is T1, but T1 is 196 newtons. Now it's a vector problem. I need to find T1 and T2. Question though, and this is a geometry. What are the angles here and here? What's the angle here?
Isn't it 60?
And the angle here?
45?
Yeah. Is that clear for everybody? Why? Should. At this level, it should. 60, 45, right? Okay. So, equilibrium, guys, means that the object is not moving. It's not moving horizontally and vertically. So, horizontally, the net force has to be 0. And vertically as well. So, I have to break T2 and T3 into components. So now I want to ask you, because we did this in chapter 1, and even chapter 2 and chapter 3, we've been talking about vectors. So let me ask you this question. What are the components of T2 on X and Y? In terms of T2, of course.
Is it 0 cos 60?
T2 cos 60.
T2 cos 60.
T2 cos 60. Very good. And what will be the Y component? T2 sine 60, right?
Mm-hmm.
Okay. So now let's do T3. But hey, T3 is acting towards the left and up as well. So what are the components of T3?
Would it be T3 cosine 45?
Yeah. And this one will be what?
T3 sine 45?
Yep. There you are. So because of equilibrium as well, the force acting towards the right has to be equal to the force acting towards the left. So your first equation is T2 cosine 60 is equal to T3 cosine 45. And then vertically, you have two forces going up and one force going down, which is 196. So we add the forces going up. T2 sine 60 plus T3 sine 45 equals to 196. That's it for the physics. Now it's math. So before I do the math, who has a question about that?
Wait, so we still didn't find the tension, right? We
No.
still have to find the tension?
We haven't. We have to do the math now.
Oh,
So
okay.
the physics is all this. Now we're gonna do math. So before I go and do that, any questions about the components, about the tensions, the diagram? Is it clear?
So wait, now we're adding those two together with the other one?
Well, yeah, so to do the math, I will write one in terms of the other one. You can use the first equation for that, and then substitute in here. So let's find T2 first and then T3, okay? So the strategy will be cosine 60, cosine 45. So what's cosine 60? It's 0.5, right? So the first equation, this one, I'm gonna write here. So yeah, T2 cosine 60 equals to T3 cosine 45. Cosine 60 is 0.5. So 0.5 T2 equals to cosine 45 is 0.77, right? Somebody check, please. So
It's 0.707.
oh, 0.71. T3. Okay. So let's say T2 or T3. Yeah, T2. T2 is, what's this over the, oh. 1.42 T3. So I have this. Now let's substitute this here. So T2 is this, right? So instead of T2, I write 1.42 T3 times sine of 60 plus T3 sine of 45 equals to 196. All right, sine 60 is 0.87. So let's do this. So that multiplied by 1.24. All this is 1.24 T3 plus, this is the same as that, 0.71 T3 equals to 196. Like terms, so 1.95 T3 is 197. Really? So 100. Exactly 100. Okay, not bad. So T3, I mean, it's close, right? Let's see. 196 over 100.5. So it's just right to, yeah, 100 newtons. 100 newtons. I found T3. Now that I have T3, I can use it to find T2 here, right? So T2 is 1.42 T3. So let's do it here. No, you cannot see that. You can see that. So here, T2 is 1.42 times 100, 142 newtons. So T2, T1, and T3. That's the first example of using free body diagram, forces, and equilibrium. I feel like most of the questions are gonna be about the math. So I would say that's what you need to practice, that's what you need to focus. All right. What's important here? This, but then this, right? The whole vectors. How to break it into components. Directions. You need to be careful with directions. You have to draw them in the right direction so you know which ones are in equilibrium with which, right? For example, this was the X. This is the Y, right? The vertical and the horizontal.
Wait, I have a question.
Yeah.
The horizontal is like the T2 cosine 60 equals to T3 cosine 45. They're equal to each other because it's in equilibrium, right?
Yes. Yeah. It's not moving. Mhm. As long as you understand the physics, practice will give you more confidence on the math. Okay. Some of you wonder, right, how I do this. So it's hard maybe at this point, and it's even harder in school, but the less you rely on a calculator and you try to do more of the algebra, the more proficient you become with this. And it's easy to double check your work. All right. You still have to use it for some of this, right? But the less you rely on the calculator, the better you become at math. That's just, that's just how it is. Any other questions? I want to do at least 2 more examples.
Wait, sorry, I'm just so confused. If they're different angles, how would the tension be the same?
They are not the same. 142, 100.
Oh, okay, wait, sorry.
That's why. That's good. If they were the same angle, the tensions would be the same. But they are not. And it makes sense. The more steeper, the more tension.
Okay, yeah, because I got confused when you set them equal to each other, so I got confused.
The components are the same, but the components depend on the angle. That's why.
Okay, thank you.
Just to add on to that, because I was a little confused on that too. I think what she's asking is technically the tension of the right minus the tension of the left is equal to 0. And then that's
Yes.
why he set them equal to each other.
Yes.
Because that's what I was having trouble catching up on.
Yeah.
Wait, can you repeat that? I'm sorry.
Yeah, no, you're good. So basically the tension of the right minus the tension of the left should be equal to 0. So all he did was move it over and equal them to each other.
Oh, okay, thank you.
Yeah, no problem.
Any other question? You're going to be doing some of this, by the way. But the difference is that in the lab, you're giving all the masses. You're giving all the tensions. So in the lab, you are going to be given the values. You just have to find the components. So you're going to be practicing that. And trust me, I'm not going to let anybody go until at least I see some of that. Is the lab, again, is not hard to do. To find the masses and all that for the equilibrium. The math that you have to do it's interesting. All right. Okay. Let's do another equilibrium example. I just remember one. I want to let you guys think about this one. Okay. This one should be easier. Yeah, I think so. But we'll see. I'll leave that in there. just in case. So another example of equilibrium. Is this. This is a wall, and you have a chain from the top. And you have a massive, like a mass, attached to that string here on the top. All right. It's not moving. It's attached like that. They just give you the angle. Let's make it 30 degrees. Of course, gravity. And they give you the weight of this. The weight of this is 2,000 newtons. If that's the weight of this, they are asking you. So if the system is in equilibrium, find the tension on the chain. And the normal on the wall. It can be the reaction as well, but this is called so this is the chain. All right, I'll give you 5 minutes. No, 5 minutes, that's too much. Yeah, no, 5 minutes. So you guys can try and do this. I will leave that in there. It will help you. So you have the normal on the wall and the tension on the chain. All right, anybody wants to start by telling what forces you have acting here and how you draw them?
Tension on the chain.
Yeah, so we start without attention here. All right, so let's do it like this. Okay, what else? What's the force that you should never forget?
Normal.
Okay, how do you draw that normal? There's a normal force, yes, it's being asked. How do you draw it? I want to see how you guys draw that.
The same direction as gravity, or is
No,
it
mm-mm.
to the right?
The normal, oh yeah, to the right. The normal is due to the wall. So think about it, right? That's like I'm leaning, right? I'm feeling a force on my arm. That's the normal. Same with this. The normal is like this. That's the normal. And then there's one more. Why is there tension on the chain?
Is it the weight?
2000. All right. So if you go to that, that's good. Did anybody figure it out how to solve it though? That's why I left that in here. How do you solve that now? How do you find N and T? Equilibrium, right? So it's not moving. Let's draw the, we have X and Y as well, right? Okay. How much is this going down?
2000.
2000. What's this? Going to the right.
The normal.
A normal. How do you draw the tension? In which quadrant? First, second, third, or fourth? In which quadrant do you draw the tension? Hmm?
Is it the first?
Fourth.
No. Second. Yeah. That's the tension. Now, what angle is this?
30.
No, it's not 30. Come on, guys. Geometry. Look at the figure. Look at the axis. Look at it. Look at it.
$45.
At 45. What's the angle here?
60?
60. Yes. Why 60? That's the x-axis, right? What's the angle here? 90. 30. How much is that? 60. That's it. And so it's easier now. Because you only have one tension. You only have one tension in an angle. So, all right. You guys tell me, what do I do now? So now that's the fifth. We have to break into components. So how do you find this and this?
T cosine of 60.
Okay. Equals 60. And what about the vertical?
T sine 60.
Okay. Now, based on the example we did before, it's in equilibrium. Which forces are in equilibrium? What equations do you write?
P sine 60 is equal to 2000.
All right. And we can solve for T now. T is 2000 over sine 60. That's the vertical. What about the horizontal? This is on Y. What about on X?
WT cross 60 is equal to normal force.
Which is what you're being asked. What's 2000 over sine 60?
I got 2,309.4.
2000,
2,309.4.
like that? That?
Yeah.
Okay. Now this is tension here. So T cosine 60 is N. So how much is N then? That divided by 2. So it's about 1,000, what? 1,150?
54.
1,154? 1,154 newtons. Normal tension. All right? So these two examples have to show you two things. The importance of angles, trigonometry, vectors that we're going to be doing still, and free body diagrams, forces, weight, tension, normal force, equilibrium. Questions?
Wait, so the free body diagram is just on a y and x axis?
Yeah, we are just basically projecting everything on the plane. Yeah.
And that's why we don't write 30 and it's 60.
Well, we don't write 30 because 30 is the angle with the vertical here. You could use 30, but which is here. But it's more convenient to use the angle with the horizontal 60. That's why.
Okay, thank you.
Okay. All right. Let's do.
Sorry, why was the tension on the second quadrant? I know because the ball is being held up, right? But then how do we know that, like, why is it on the left and not the first one?
Because this is leaning like this. So you just basically move this here. Like a vector, remember? You don't change the direction of a vector. You keep it. That's
Oh, I see. But if like the diagram were to have the wall on the right, then it would be on the first quadrant.
if the what?
If the wall was on the right side, then would it be on the
Oh yeah, it will be like this.
Yeah, it would be on the first. Okay, just checking. Okay, thank you.
Let's do an example now in motion. Okay. So let's do the pulley system. Okay, because that's also important. And that will be the last example of today. Tomorrow, important. Tomorrow I'm gonna do full class on examples. Okay. I will do outdoor machine. I will do one more of this. I will do incline planes, and I will do more than one mass. Right now we're just doing one mass. There's 2 free masses, so we will do that. That's tomorrow. Now, if you are interested, I will show you after this example I'm gonna do a whole video I have in there where I go over examples, situations. All right, so that help you a lot. Okay, so let's do the situation I showed you before, a horizontal table, a wall or a vertical, a pulley, and then you have one mass, M1, with a rope or a rope, and then you have another mass, and the classic example is you're gonna calculate the acceleration of the system and the tension on the rope. So calculate the acceleration of the system and the tension. All right. Guys, you have it, I'm pretty sure. Start with the, oh, I have to get the masses. Start with the free body data. M1 is 30 kilograms and M2 is 10 kilograms. Ignore friction. We're gonna do the same with friction later on. For now, no friction. Right, so that's 30, that's 10. Is Manahil in class? Manahil? Mohammed? Sridhar? Vish? Shalibit Adler? Alan? Sama? Oh, okay. Okay. So, what are the forces acting? Let's start with M2. What's acting on M2?
Weight.
So, W2. How much is W2?
98.
Nice. 10 times 9.8. 98 newtons. All right. What else is acting here?
Tension.
Tension. Very good. What about M1?
Normal.
What else?
Weight.
Weight 1, which is how much?
294.
Yeah. And what else?
Tension.
Tension. Good. Same tension because that's an ideal pulley. All right, guys. So that's the first step. Is that clear for everybody? It's good? Okay. Why is there an acceleration? Think about Newton's second law. Why is the system moving?
Because it has a force acting on it.
The net force equals to mass times acceleration, right? Yeah. So, M2, in which direction is it moving?
Down.
Down. Because of this, right? 98. But wait a second though. What about the tension? The tension is dragging it. Right? It's like stopping it. So what's the net force acting on M2?
Would it be 0?
98. Minus what?
T.
Yes. So for M2, the net force is 98 minus T equals to mass 10 times acceleration. Guys, Newton's second law. For M2. For M1, why is M1 moving to the right? Because if M2 is going down, M1 is going to the right. Why? What's pushing or pulling M1?
Tension?
Tension. That's the net force. There's no friction, so that's it. That's equal to what? Mass M1 times acceleration. There you are. That's the physics. Now we have to solve the system of equations. Now that's easy to solve. Because look, 98 minus t equals to 10a, t equals to 38. So you can substitute. You can write this. 98 minus 30a equals to 10a, and we solve for a, right? 98 equals to 40a. So the acceleration is 2.5 meters per second squared. Right? Yeah. And if that's acceleration, I can find the tension. Tension is 30 times 2.5. That's 70. 70 newtons. Yeah. All right, guys. That's a moving type of problem where we use Newton's second law. All right, here. So we're gonna finish with this, but what you're gonna do besides this, right, is you're gonna, is if you have time, hopefully before class tomorrow, you're gonna watch the following video. Oh, there's two videos. Oh, one video. Okay, so this is I'm just letting you guys finish writing down, calculating that. All right. Any questions, by the way, before I show you the video?
So wait, how did you get the equations for M2 and M1?
Force equals to mass times acceleration. Force equals to mass times acceleration.
Oh, so the tension is the force, right?
Yeah, yeah.
Okay.
Yeah.
Okay, I thought you were multiplying the tension by the mass of M2. I was confused with that. Wait, it's M2 times acceleration is equal to the tension?
No, it's a colon.
Oh, it's colon. Okay, I couldn't see because of the light.
Oh, this. Let's just... There.
I do have a quick question as well. So in this case, would the tension from both sides be 70? It would be the same tension
Yeah.
for both?
Yeah, the same
The whole
tension.
thing?
Yeah.
Is that the same for like every type of example like this, the pulley?
Oh, no.
The tension would be the same? No?
No. We're gonna do one tomorrow, the other machine, when they are not the same.
Okay. What makes it the same in this one?
The pulley is just one pulley. If I give you two pulleys, you have more ropes, so that's different.
Okay.
And also, we assume there is no friction on the pulley. So in chapter 8, or not, no, yeah, chapter 8, we're gonna do problems like this again, where there is friction on the pulley. That makes things even more interesting. You see, that the thing about physics is that we start adding more factors in the equation to make things more realistic. We and at some point, like if any of you one day take classical mechanics, we add air drag. We can add, we're gonna add friction. And yeah, we start adding